Hi, welcome to video on BJT. In this video, we'll see the applications of BJT as a switch and as an amplifier. Before we start, let us look at the prerequisites. You should be knowing what is Ohm's law, Kirchhoff law, Kirchhoff voltage and current laws. You should be knowing what is semiconductor p junction, and of course the BJT functioning you should be knowing. Okay, these are some prerequisites. So let us start with BJT, that is bipolar junction transistor as a switch now. This is what a switch means. Now, suppose you have an LED. Assume that I have a LED, which is okay. Assume that I'm applying a voltage of around 5 volts. So 5 volt is applied. So when the okay, this is LED, and assume that I'm having a current limiting resistor here. When the switch is open, the LED is, so this is switch condition, and the LED condition. So when the switch is open, LED is off, it is not glowing. And the switch is closed, when the switch is closed, so if I close this, so this will be get forward bias and this will be on, so this is what is switch means. So, and of course there is no voltage drop across this switch, it's almost a zero. And let us see how do we use transistor as a switch. Assume that let us assume a value of R with this 5 volts. So it requires around 25 milliamperes of current to give a very glowing light. So assume that that is the minimum requirement. Now if I want to use BJT to deliver a current of 25 milliampere through the LED when it should be glowing, and it should be zero current when it is when you don't want to glow. So for that, let me consider this BJT, and this is the RB resistor which will going to control my current to this one. So this is IB, and so let me put the LED here. So this is what is LED. Now this is VCC. This is, let us assume that this is R value, and assume that this is LED. And let me have the output from a particular sensor. So assume that you have a sensor. It can be a PIR sensor, which stands for proximity infrared sensor. This is proximity IR sensor, meaning if any disturbance happens close to this, so it will going to give output of high. When there is a disturbance happens. If there is no disturbance, it will be giving a low. When it is low, it is 0 volt. When it is high, assume that this is 3.2 volt. Assume that it is 3.2 volt. And of course, this will be connected to 5 volt and ground volt for its operation. This is a typical sensor. Assume that this output is given to this. Now, what should happen? When there is a person detected, the LED should glow. When there is no person detected, when there is no person close to this sensor, the light should be off. Now we know that when there is no person, it is zero. When it is zero here, let me ground this. When it is zero here, IB is zero. When okay, this is the person is not there. When the person is not there, when he is not there, IB is 0 because this is low. When IB is 0, we know that IC is equal to beta times IB, and so since IB is 0, this is beta times IB, or we also know that okay, this is also equal to IS e power VB by VT. So these are the two equations which are deciding the value of IC. Now since IB is 0, this will be 0. So LED condition is LED is off. So that is what is we want. So when no person is there, the LED should be off. Assume that a person comes. So yes, there is a person detected. Whenever there is a person detected, we will going to have some voltage. Let me say it as Vx. Vx was earlier 0 volt. Now Vx is 3.2 volt. Now, if you want to have a current of 25 milliamperes of current should flow through this, so that it flows sufficiently uh, with greater density, or with good glowing condition. So then for a IC of 25 milliamperes, let us assume that IS of this particular BJT is 1 into 10 power minus 13 amperes. Let us assume that beta of this is 100. So now to have this much current, using this equation of IC is equal to IS e power VBE by VT, I can write the expression for VBE as VT times ln of IC by IS. So now I know that VT is 26 millivolt, which is thermal voltage. ln of I want 25 milliamperes to flow, divided by, this is just an example. So this may require certainly less than that current, and this is 1 into 10 power minus 13 amperes. If you find this ratio, this comes out to be, so it is 26 exponential of minus 3 into ln of 1, sorry, 25 exponential of minus 3 divided by 1 exponential of minus 13 close equals, can you see you require a VB of 682.3 millivolt. So this is the voltage that is required. So you should require 0.68 volt here. So can I calculate what is okay, from this? Do we know what is IB also? IB is equal to IC by beta, which is 25 milli divided by 100. That is now 25 exponential minus 3 divided by 100 is 250 microampere. 250 microampere. So IB should be 250 microampere, 3.2 volt as a high voltage. So now can we write what is RB is equal to Vx minus VBE. Vx is this voltage, VB is this voltage divided by IB. So can I write it as 3.2 minus 0.682 by, this is 350 microampere. So now that is whole inverse into 3.2 minus 0.682. Can you see now this comes out to be 10 kilo ohm. So this is 10.072 kilo ohm. So you require 10 kilo ohm as the resistance. If you connect 10 kilo ohm here, when the sensor output is high, you will get 250 microampere here. Since the beta of this is 100, I will get 25 milliampere flowing through this. Then this LED close. This LED close. So now we know that when the voltage is 0, it's in cutoff region. The BJT is in cutoff region. Cutoff region. When you have 3.2 volt, when you have 3.2 volt, we know that okay, this is VCE and this is IC. So this is your cutoff region where the IC is 0. And when you get some certain voltage, then it operates somewhere here. Now, if this voltage drop VCE, suppose if it is around 0.2, then this will be in saturation region. This is saturation region. Suppose if this voltage is something like okay 2 volt, 1 volt or 0.8 volt, then this will be in active region. So for the BJT to act like switch, the BJT to act like switch, it should be in cut off region is one possible one must region. When it is 0, it should be in cutoff. So that is the off condition. When it is on condition, it can be either in saturation region or active active region. Meaning, if the voltage is slightly more than 0.2, then the BJT is operating in active region. If it is in terms of less than, slightly less than 0.2, like okay, 0.18, 0.15 volts, then it is in saturation region. So basically, uh, BJT as a switch, as a switch will operate in cut off region or or saturation or active. Even if it is in active region, BJT is on. BJT is on. So this is active and saturation. This is like okay, this is for off, this is for on. When it is either in saturation or active region, the BJT is on. So this is about BJT as a switch. Now let us move on to BJT to amplify small signal, small AC signal. This is the requirement. So now you have the BJT. This, assume that you have this BJT, and then you have this small signal, small AC signal. This is small AC signal. When you say small AC signal, we are referring to okay, AC signal means this is zero. This will be varying around zero, varying around zero. So let us consider a sinusoidal signal. Sinusoidal signal. Since it is small, this amplitude from zero, this will be maybe in terms of 100 millivolt, 10 millivolt, or maybe because it may be 5 millivolt also, or it can be 150 millivolt also. You see, now it is in terms of 150 millivolts range. Since it is around zero, this can go to minus 100 millivolt. It can go to minus 5 millivolt. This is the negative maximum possible. Suppose you connect this directly to this BJT, and suppose you have some resistor here and you have this VCC which is of 5 volt. Let me say this is RC because this is collector, this is base, this is emitter. Let me ground this. We know that this is a NPN transistor. When you have a PN, can you really think of a diode like connection existing between base and emitter? So basically there will be a N junction between base and emitter. There will also be a N junction between collector and base and collector. Now let us try to see if you apply this signal, what happens to this PN junction. So we know that PN junction will have a IV characteristics, something like this, correct? So this is voltage across that diode, and this is the current to the diode. Will you end up with something like these are the characteristics? So only when the input voltage, when the voltage across the PN junction is more than V gamma, which will be typically 0.56, 0.5 or 0.6 or 0.62. So this is the typical range of your V gamma. If it is more than that, only the current flows. Suppose if the voltage is 10 millivolt, 100 millivolt is like okay 0.1, 5 millivolt is 0.05, 50 is 0.15. So you can see all these voltages are far less than this, meaning you are operating somewhere here. So you are operating somewhere here. When you are operating somewhere here, what is this ID? So the ID is 0. So now ID matlab diode current. So now we are not referring to diode current, we are now referring to base current. What is the base current when you are operating here? The base current is 0 because for these voltages IB is 0. When IB is 0, know that current IC is nothing but uh, beta times IC. So this is beta times IB, beta times IB. When IB itself is 0, then IC naturally is 0. So you won't get any current. Meaning this small signal, small AC signal of magnitude even 200 millivolt, 300 millivolt cannot be applied directly to this BJT for amplification. So this cannot be an amplifier. meaning BJT the BJT, if you apply the AC signal as it is, it won't amplify. It won't amplify. Then what to do now? We have to suppose instead of applying the input signal somewhere here, applying the input signal around 0, if I apply the input signal somewhere here, now you can see, assume that here I have voltage of 0.56. Now with this 0.56, if I just vary it around, can you see the voltage varies from this to this? You see you're going to have a different base current. Can you see the IB changes from here to here as your input voltage changes? So there is a change in the base current due to the applied voltage provided this input AC signal is shifted from 0 to 0.56. How this shifting can be done, how this movement, how do I level shift this input signal from this to this, that is known as biasing. So this is okay, this is biasing of BJT. The purpose of biasing is to make my input voltage sufficiently DC shifted so that this can have some appreciable change in the current that going to flow as the input voltage changes. So that is the purpose. Now, how do we achieve this movement from this to this? So that can be achieved using biasing circuit. So now let us see how do we do this biasing. So let us see how do we achieve this biasing of BJT. So for that, so now we have this BJT. So now I need to bias the transistor. So now you have this BJT here. Now this resistor R1, let me name it as R1, let me name it as R2. Let me connect this junction to base. Let me ground this. Let me connect this to VCC. This is VCC. Now, can you see this R1, R2 and VCC will give me some voltage, some Vx. So what is the voltage Vx? That Vx is nothing but the current flowing through this multiplied by resistance. So shall I say? So what we'll assume that we will assume the current flowing through this is almost zero. Of course, it will be very few microampere, which will be negligible compared to this current that is flowing here. Assuming this as zero current, so what is Vx is equal to voltage at this point is current multiplied by resistance R2. So what is this current? This current is the whole current flowing from this to this, which is nothing but voltage difference between this and this divided by the overall resistance. Is it not VCC divided by R1 plus R2 is your I multiplied by R2. Is this Vx? This is the voltage at this point with respect to ground. Suppose if I ground this, is this Vx itself is VB? This Vx is VB. Now, what is this VB? This is equal to VCC R2 by R1 plus R2. Why require this VB of this much? So that this shifts shift the input signal variation around 0. From here to shift it means you have to have this bias voltage so that this voltage is whatever the required voltage. Now I have the AC signal. Here. So let us assume that this is 0.586 volt, so that or 5986. Okay, this is 0.5986 volt. So that IC of 1 milliampere flow, meaning for a IC of 1 milliamperes, using the equation IC is equal to Is e power VBE by VT. The VBE becomes VT times ln of IC by IS, which will be 598.6 millivolts. So this is what is VBE, so that a current of 1 milliampere flows through the, this is 1 milliampere, so that this voltage is 598.6 millivolts. How you are achieving this? That is achieved using R1 and R2. So of course, we can assume the value of R1 as 100 kilo ohm. You can find the value of R2. Now what you have from this equation, it is 0.5986 is equal to 5 into R2 divided by 100k plus R2. You can actually solve for R2, where R2 is equal to, can I solve? I can solve this 0.5986 alpha equals, it is 5 into alpha A divided by 100 exponential of 3 plus alpha A, close, shift calculate. You can see I'm getting the value of R2 as 13.6 kilo ohm. Now I will use this as 100k. If I use 13.6 kilo ohm, I will get 0.56, the current of 1 milliampere flow. So let us find out what is RC later. Now this is your okay, biasing done. So once the biasing is done, now I need to apply the AC signal. So this is your VN, the AC signal. To apply AC signal, I cannot directly connect this AC signal as it is, because this may have some DC component. This DC should not be affecting this voltage, so that I will use a coupling capacitor. So this is CC. The purpose of using this coupling capacitor, it is called as coupling capacitor. So we know that XC, that is the reactance of a capacitor, is given by 1 over 2 pi RC, 2 pi, sorry, FC. So now assume that it has got some DC. If it has got some DC, is the frequency 0? Then what is the XC of this capacitor for a DC signal? So now the XC of a capacitor is infinite for a frequency of 0, meaning this, if at all, if it has got some DC component, it will not be reaching this point, so that this is not affected. So this coupling capacitor is used to block the DC in the input. If at all, if it has got some any DC component in the input, it will block. So it is effectively blocking. How about allowing the AC signal? Assume that the frequency is around 10 kilohertz. When the frequency is more, you can see X is less. This easily couples the signal. So that's why this is called as coupling capacitor. It couples the AC signal. This will couple the AC input to amplifier input side. So this AC input is coupled to amplifier input. So that is the purpose of your coupling capacitor. So now, where is the input swinging? The input is not swinging anymore at 0. Now it is swinging at, if this is VBE, if this is IC, then it is swinging around 0.598 volts. It is swinging around that point. So when it is swinging around that point, you will naturally get, okay, let me just write it here, you will naturally get a huge change in IC voltage. So what we'll do now is, we'll take a small example of a sine wave and try to see how the amplification occurs. Let us also understand, if this VCC is 5 volt, if it is 1 milliampere, let us assume that you have a resistance of 2.5 kilo ohm connected here. If you are having a 2.5 kilo ohm connected here, this is plus minus, which is VCE. I can write a KVL expression for this. So I can, of course, I can write this as a VCC, something like this. So I can write a KVL here. This is minus plus, this is plus minus, this is again plus minus. So this is actually VCC. So instead of writing VCC here, I can write a battery here. So what is the KVL expression? KVL expression goes, this is voltage rise. So it is plus of VCC. Can you see there is a voltage drop minus, what is the current? It is capital IC into RC. Then can you see is it again plus minus, again voltage drop minus VCE is equal to 0. So now I want to know what is VCE is. VC is equal to VCC minus ICRC. So how much is VCC? This is 5 volt minus of 1 milli into 2.5 K. This K and milli will go off. So you have 5 minus 2.5, which is nothing but 2.5 volt. So this is VCE. So you have a VCE of 2.5 volt and you have a IC of 1 milliampere. This is called as biasing condition, which we also call it as Q point. Q point of the BJT, which is nothing but ICQ and VCQ. So now what is that point? It is actually 1 milliampere, 2.5. So this is the biasing. After biasing, I'm having these things. Now, with these conditions, so now let us apply the input voltage of something like this. So this is 10 millivolt. Assume that this is minus 10 millivolt. So can you see, is this signal applied over here? When it comes over here, is this actually 598 millivolt plus of this sine wave, because this is the DC. Due to VCC and R1 and R2, I'm getting 589.6 millivolt. And because of this input voltage, this is going up. So at this point, what are the voltage? This is it is it not 608 millivolt, and is the voltage here is 588 millivolt. This is actual base voltage VBE plus VN, because I'm coupling the signal to this. So this is the voltage what we have. So for these voltages, now it is not only these two voltages, it is reaching from 598 to that voltage. It is gradually changing. So let us make a list of what is IB, what is all those voltages, and try to find out what is this is what is V in. So VBE is constant at 598.6 millivolt. So assume that if the input is 0, this is V in is 0, 0 plus 598.6 millivolt. And what is IC? IC is nothing but IS e power VBE by VT. And I say VBE, it is this plus this. So, and then what is VCE? VCE is nothing but VCC minus ICRC. So let me just keep finding the thing. Let me first find for different values. So this is 0 millivolt. Let me say 2 millivolt. Let me say 5 millivolt. Let me say 7 millivolt. Let me say 10 millivolt. And this will again repeat. So it's again 7 milli, 5 milli, 2 milli, 0 milli, and then minus 2 milli. This is minus 5 milli, minus 7 milli, then minus 10 milli. This will again minus 7 milli, minus 5 milli. This is like minus 2 milli and 0 milli. You see, this has completed one cycle, 0 to 10 milli, back to minus 10 milli, and back to 0. So this is the overall sine wave change, sine wave variation. Can we find the corresponding IC? So what does this will end up with this? This is how much is this? 600.6. This is 603.6. This is 605.6. This is 608.6. This is the same value, so this will repeat here. So this again repeats here. This and these two are same, and these two are same, and these two are same, and then you have this is 598 again. Then here it is 596.6. This is 593.6. So this is 591.6. This is 588.6. Then this repeats here. Then you can see this repeats and this again repeats. So let me find what is IC. So what is IC in the first case? I think it will be 1 milliampere. Let me just redo it. It is 1 exponential of minus 13 into alpha e to the power of VB by VT. So it is 598.6 divided by 26. Okay, let me put this as okay. What is this? It is this much. So it is 997.2 microampere, almost close to 1 milliampere. Next it is, I will make this 600. This is 600. You can see now it is 1.07 milliamperes. Now it is 603. Correct? It is 603. I'm trying to find for different input voltages what will be the current. The current is 1.208 milli, and if it is 605, it is 1.3 milliamperes. If it is 608, sorry, if it is 608, it is 1.46 milli. If it is, okay, what I'll do, I change this to 6 after. Okay, this repeats. You can see now it is 1.3, 1.208, then you can see 1.07, then it is 997.2 micro. These are all milli. And then 596. Let me make this 596. It is 923 micro. Then it is 593. I will make it 593. It is 822 micro. Then it is 591. 591 is 761 micro. Then it is 588. 88. See, it is 678.8 micro. This is the variation in collector current. So this variation in collector current, okay, let me repeat this. Is it 761 micro? This is 822 micro. This is 923 microampere, and for 0 it is 997 microampere. So these are all currents. Now let me find out what will be the VCE for this. So VCE, I know that it is 5 minus alpha A into 2.5 exponential of 3. Let me calculate for 997.2 exponential of minus 6. Can you see now this is 2.507 volt, that is VCE, and for 1.07 exponential of minus 3 it is 2.325, and then for 1.208 exponential of minus 3 it is 1.98 volts. Then for 1.3 exponential of minus 3 it is 1.75. For 1.46 exponential of minus 3 it is 1.35. 1.75, 1.98, then it is 2.325. 5, then it is 2.507. So let us do it for 9, 23 exponential of minus 6. Then it is 2.69. Then calculate for 822 exponential of minus 6. Then it is 2.945. Calculate for 761 exponential of minus 6. It is 3.09 volt. Calculate for 678.8 exponential of minus 6. If it is 3.30 volt, then this repeats 3.09, then it is 2.94, then it is 2.507, then it is 2.3, sorry, this is 2. I missed out somewhere here. So this is 2.69 and this is 2.507. Okay, what is this we have done so far is when the input voltage varies from 0 to 10 millivolt and back to minus 10 millivolt when it like happens like this. Can you see the output voltage is also changing? Now what we are trying to observe here is when the input voltage changes, this is 598.6 millivolt is your VBE. Over and above this, if your input voltage changes to, if this is like okay, plus 10 millivolt and minus 10 millivolt, over and above this is V in. Is output changing? Output is changing around 2.5. You can see it is okay. Let me just write 2.5 somewhere here. So from 2.5, can you see from 2.5 and the input voltage is increasing, it's actually reducing. Can you see this is reducing? This is going up to, this is going up to what value? Can you see the least voltage is 1.35? Can you see this goes up to 1.35? This is 1.35 and it again goes back to this. And when this is at the minimum, see when this is minus 10, you have 3.3. Can you see this goes up to 3.3? This is minimum, it is 3.3. So this is 3.3. So what is the swing? It is varying from 3.3 to 1.35. So this is the change in your VCE for a change in input voltage from 10 millivolt to minus 10 millivolt. So what is the change in, what is the delta V naught? So delta V naught is 3.3 minus 1.35. What is delta V in? This change in V in, it is 10 milli to minus 10 milli. So how much is this 1 point, that is 3.3 minus of 1.35? Can you say it is 1.95 and 1.95 divided by 20? So 1.95 divided by 20 milli. Can you see this is 20 milli? So this is what? Change in V naught to change in V in. So is it not 97.5 is the change in your output voltage compared to input voltage? This we call it as gain of the amplifier. So what is the gain of the amplifier? So how did we got the gain of the amplifier? We literally varied the input voltage around 598.6 millivolt, which was resulting in almost 1 milliampere. When the input changes due to, sorry, when the VBE changes due to the input voltage from 0 to 10 milli, again back to 0, then gone to minus 10 and then gone to 0. This entire swing, the output is swinging in the opposite direction. Can you see the output is swinging in the opposite direction? Is it not around 2.5 volt it is swinging? So at this point, that is at the collector point, the input is swinging in, it is going above and down, so this will actually go below and up. So this is out of phase. By what is the gain of the amplifier? Gain of the amplifier is 97.5 is the gain of the amplifier. So this is how we found gain of the amplifier as 97.5. And since you can see this is going opposite direction, the output is said to be out of phase, out of phase with out of phase with the input. So here you can see input is coupled to this amplifier using capacitors and resistors. So that's why the name of this amplifier is RC coupled amplifier. This is the name of the amplifier. What is the name of the amplifier? It is RC coupled. Why it is RC coupled? Resistors and capacitors are used to couple the input AC signal to this amplifier. That's why it is called as RC coupled amplifier. Okay, so this is how RC coupled amplifier will amplify. You see, this is exaggeratively I have written this waveform, but typically if the input waveform is varying like this, around 0, the output will vary at 2.5, something like this. Can you see this is the actual variation? This is 100 times, close to 100 times that of the variation. Since I'm not, of course, this is still I'm not representing 100 times. So if it is to be 100 times, it looks like this. So it is only small variation. This variation is huge. So this is varying around the VCE value, which is the biasing condition at 2.5, and this is your input voltage, and it is out of phase. Why it is out of phase means, as you know that VCE is equal to VCC minus ICRC. As the input voltage increases, this increases. Because this is constant, this has to reduce. This has to reduce. So that's why it is reduced. Can you see this is reducing? Because when this increases, IC increases. When IC increases, this has to reduce. This has to reduce. The vice versa is, when the input voltage reduces, IC will reduce. When IC reduces, this will increase. This will increase. You can see when this is going down, this is going up. It's as simple as that. Okay, in the next video, we will see some more details of this amplifier. So we'll get an expression for gain of the amplifier and all those things. Thank you.